We're going to broaden our look into energy in Chapter 8 by introducing the idea of potential energy, and that will eventually lead us to the concept of conservation of energy. Just to recap, in Chapter 7, we introduced the idea of work. Work is what a force does when it's applied to an object and that object undergoes some sort of displacement. And we learned that, of course, that the displacement has to be at least in the direction or anti-parallel to the force, or there has to be at least a component of force in the direction of the displacement in order for work to be done. Then we said, well, okay, well, if work is the product of a force and a displacement, if you apply a force, Newton's laws tell us that there should be an acceleration. And so we took another look at the calculation of work through the integration and found that we could actually come up with this other term that was related to work that was called kinetic energy, the energy of motion. So we were able to link work and kinetic energy. So we're going to go one step further by introducing a new type of energy, which is called potential energy. What we're really trying to do is to get to a point where everything that we're thinking about energy transfer. That's what's going to happen when we introduce the conservation of energy. But first we need this idea of potential energy. So what is potential energy? So there's a couple different ways to think about potential energy. When I think of it, I think really of stored energy. It's when a system has this energy available, so it's kind of like having money in the bank, except you have energy in your storage. It turns out that when we look at potential energy functions, that is how we calculate potential energy, it always depends on position or where an object is or a particle is at a particular location. So sometimes potential energy is also thought of as being the energy of position. Finally, the reason we call it potential energy and think of it as being stored is that it's this reservoir of energy that the system has that would be available to convert into kinetic energy. So we could use this energy to create some motion. And so those are different ways that we can think about potential energy. So we're thinking of potential energy as stored energy that can be converted into motion, or alternatively can be used to do work, and also that it's an energy of position. So it has to do with where an object is, where a particle is in the system that allows it to have this potential energy. So if we look at the work kinetic energy theorem again, we can sort of combine it and sort of add this idea of potential energy. So let's remind ourselves about the work kinetic energy theorem. So we calculated work was, in the most broad definition, was the integral of a force over a displacement. And we were able to find that this was equal to a change in kinetic energy. So, for instance, if I push on a box and I push it across the floor, as I'm applying that force to make it move, that force through Newton's second law should probably also cause an acceleration, if indeed it's an unbalanced force. And so if it has an acceleration, we expect the velocity to change. And so we were able to sort of manipulate this expression and come up with the fact that the work done on a system creates a change in kinetic energy. We called kinetic energy the energy of motion because it's equal to 1/2 mv squared. So you don't have any kinetic energy unless you're moving. And so by doing the work, we create the motion and we create this kinetic energy. But instead of thinking of this from the viewpoint of I did work, what if we really sort of tried to keep ourselves to this discussion of energy. So if all of a sudden I have this increase in kinetic energy, what happened? Where did that energy come from? And so now if you start thinking about the fact that we've been calling the potential energy stored energy, that seems to be a likely location or a likely source of the kinetic energy. So what if the kinetic energy that we see manifested as the object speeds up, what if that energy came from energy that the system had stored, specifically stored in what we are calling potential energy? And if we think about that, as the kinetic energy increases, so remember, change, delta K, which is change in kinetic energy, is always the final kinetic energy minus initial. Anytime you see change, it's always final minus initial. So if we know that the kinetic energy went up, it seems to reason that at the same time, the potential energy went down. So an increase in kinetic energy should be accompanied by a decrease in potential energy. And we're going to call this U. U is going to be our term for potential energy. And the way we can write this is minus a change in U, because the idea is that overall, if the kinetic energy increased, then the change in potential energy should be negative because it's going down. But to make these two sides equivalent, we put in that negative sign. And so this is going to start to be a focus for us, this relationship between kinetic energy and potential energy. In the next videos, we're going to come up with expressions for potential energy for specific forces, namely gravity and the force of a spring. And when we do that calculation, it might become more clear that at the same time as when we're finding the work, we get an increase in kinetic energy. We're going to see where this, the fact that there's minus the change in potential energy is also equal to the work. In a sense, what we're saying is the reason we can do the work is because we use stored energy to do it. So as the stored energy is used up, work is done. So I really want you to try to wrangle with these ideas of energy being transferred from one type to another, because it will make everything a little bit easier to understand as we use this energy approach in this unit.